Okay, so when we do these Lewis structures, there are rules that you have to follow and some things that you have to know how to calculate. So we're going to spend some time with that today. So let's start by looking at the rules. The first thing you're going to do, and I've said this, we just haven't written it down. The first thing you're going to do is calculate. And when I say calculate, I mean sum the total number of valence electrons for all the atoms in the bonded compound that you're dealing with. So you're going to take each piece, figure out how many valence electrons each piece has, and then you're going to add all those together, and that tells you how many you have to work with. So once you figure that out, then you're going to write your atoms, or I guess I should say write the symbols. For the atoms, and that will show how the atoms attach to each other. And this will be with a single bond. So you start with a single bond. Now some things to help you out here. Often, or not most times, when you're given the chemical formula, it's written in the order the atoms attach most of the time. Then we have to remember certain things. You know, like carbon has 4 sites for attachment, so it makes sense for it to be a central atom. You have to remember things like that. If I look at an example here, HCN, my atom in the middle is carbon, so it's telling me that my carbon is bonded to my H and my N. This formula is written in the way that I would draw this formula.
After you have connect with a single, is that supposed to be a single bond or just a single?
Oh yeah, this would with a single bond, sorry. Good question, Kira. Okay, so this is when we're talking about a molecular compound. Remember, we've already talked about polyatomic ions and how a polyatomic ion can actually be covalent bonded but still be an ion with a charge. So if we're looking at a polyatomic ion, or I could call something a polyatomic molecule as well. When I'm dealing with something like this, most often the central atom is written first. So let's look at an example of a polyatomic ion. Let's say I'm going to deal with carbonate. What's the formula for the polyatomic ion carbonate? You should know that. What'd you say, Haley? CO3 2 minus. Do you guys agree with her? Yeah, she's right. Okay, so what does that tell me is the central atom? It tells me my carbon will be the central atom. So once I see this, I'm going to find my total number of electrons, and then I look at my charge, and I'm going to add or subtract according to charge. So in this case, I would find the total. So this would be total plus 2 electrons because I have a 2 minus charge. So I can't forget that. So that's my polyatomic ion. Then if I look at a polyatomic molecule, like let's say I have SF4, I follow a rule that the central atom, I mean there are some key clues here. If I have 4 of these and 1 of these, it stands to reason what's going to be my central atom. But the central atom is normally or generally less electronegative than the atoms that go around it. And if I look at that, would you agree that sulfur is less electronegative than fluorine? Yeah, we should know that because fluorine is what? What's true about fluorine? What'd you say, Kira?
It's most electronegative.
Most electronegative element on the periodic table. So that should be an easy one to figure out. Every once in a while you'll need a little more info before you draw a Lewis structure, so you have to stop and look at those things. It won't be blatantly obvious when you see the formula. As we move on, the first thing we do after we've put them together with single bonds is we're going to complete the octets around all the atoms that surround the central atom. One thing you need to remember here, which I think you will, but remember about hydrogen. It only wants 2 electrons, so don't give hydrogen an octet. It's only going to have a pair of electrons either shared or around it. Once I've done that, once everybody has an octet, I place the remaining electrons on the central atom. And this is important to remember. Even if doing so results in more than an octet, because remember we've already talked about the fact that some of the atoms have expanded octets. You've got a little list of those already, like sulfur, phosphorus. So up until we get to this part, it's pretty easy. You don't have to think a whole bunch about it. Then it can become a little more of a puzzle. So, do you have any suggestions about what I might do if my central atom does not have an octet and it needs an octet? What could I possibly do? Say that again? Share more electrons. I can move electrons around. Remember how we talked before about the fact that I have to pay attention to the total? I don't have to pay attention to so much every individual atom. I need to be sure they all have their octet, but I can move the electrons wherever I want. So let's make a number 5. If there are not enough electrons to give the central atom an octet, I would say try multiple bonds. And you can think of that as sharing. You can use one or more of the unshared pairs of electrons on the central atom. So you can move them if you need to. I could do double bonds. I could do triple bonds. If I need to. So once I've done that and I feel like everybody's octet is satisfied, I'm going to do a check. Take an outer shell count. Of electrons and make sure it equals what it's supposed to, and then check, are all atoms satisfied? So you have to ask yourself those questions. Now let's look at a couple. So you've got a couple examples in your notes. Let's look at PCl3. So the first thing you're going to do is find total number of electrons. Take a minute and do that. What's my total number of electrons? How many electrons does phosphorus have? 5, okay. Jackson, how many electrons does chlorine have? 7. So I have 5 plus 21, or a total of 26 electrons. Is this a polyatomic ion? Do you recognize it as a polyatomic ion, or is it a molecular compound? It's a molecular compound, right. So I don't have to add any electrons. I know I have 26 to work with. I have a singleton, which is my phosphorus, so I will make that my central atom. And then I'm going to attach by a single bond each chlorine. So I've used 2, 4, 6 electrons. Now I'm going to go through and I'm going to fill my octet for each chlorine. So 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used 24 of my 26 electrons. Do all atoms have an octet? What's wrong with it, Haley? My phosphorus needs its last 2 electrons, and guess what? I have them left. Now, it's a good idea when you do this to go back in and kind of check. Okay, I have 8 electrons here. I have 8 here. I have 8 here. And I have 8 here. So the octet rule is satisfied for each atom, correct? How many total shared electrons do I have? What? Somebody said it. Was it you? 6. Haley says 6. So I can say how many shared pairs, how many unshared pairs, how many single bonds. You can ask all those kind of questions.
Why did you choose to put the CL on like the right, the left, and the bottom?
Because I know more about molecular geometry than you do, but you'll know here shortly. When we finish this stuff up, we move right into it. Okay, so let's look at this compound. CH2Cl2. Let's have you work all the way through that. See what you come up with. When you have a structure, stand up. How many total electrons did you have to work with? 20, good. Take your drawing and check with partner. See if yours looks like somebody else's. Then see if yours looks like mine. Or close to it. Did you check for octets? Does hydrogen have an octet? Why'd you do that, Kira? Because it only has 2, right? But is it satisfied? Yes. Okay, I'm going to give you one that's harder. Let's see. Let's have you, and I want you to get together with your lab partner and do this. Draw HCN. I want the Lewis structure for HCN. So move to your stations, work through this one together. So how about try it by yourself and check with your partner and see if they look alike. How many total electrons do you have to work with? 10. Okay. When you're done, come back. Do yours look alike, Haley, Kira? Do they look the same? You guys look alike, Caitlin, Evan? Well, what are you doing, Evan? Oh. Kira, Seneca, you guys look alike? Yeah? How about you two? Yes. Luke, Carly, you good? Do yours look alike? Exactly. All right. So when I do this, I had 10 electrons to work with. I'm going to put my carbon down. I'm going to single bond it to H. And then I'm going to bond it to nitrogen. And I've used 4. I look at this and I say, gosh, nitrogen still needs some electrons and carbon still needs electrons. Carbon's got 4. Needs 4 more. So I'm going to triple bond it. Since I've used 2, 4, 6, 8, nitrogen still needs 2, so I stuck them over here on the side. Does yours look similar to that? Okay, good. All right, so now some Lewis structures have more than one possible structure. We have to figure out which is the best. So we're going to talk about something called formal charge and alternate Lewis structures. So I'm going to say sometimes it's possible to draw two or more valid, what we would call valid Lewis structures. They're valid because they all obey the octet rule. So you will find there may be a time where you draw a structure one way and your partner draws it another way, but both of them are valid because everybody has the amount of electrons that they want. So how we think of this is we think of these technically as all the structures that contribute or are contributing to the actual arrangement of electrons. So they all contribute to what the valid Lewis structure might be, but I would say, but not all contribute in the same extent. So we have to find a way to figure out which one is the most valid, or which one's the most important. So we have to ask ourselves, how are we going to figure out which of the structures is the most important? And to do this, we use what is called a bookkeeping method. Of valence electrons, and it is called formal charge. And I will give you a definition for formal charge. We'll say the formal charge of an atom in a molecule. So we have to realize when I say that much that we're talking about each piece of the compound or of the molecule or of the polyatomic ion. Is the charge the atom would have if each bonding electron pair in the molecule or ion were shared equally. And we already know, because we've talked about this, they're not always shared equally between two atoms. So we have to look at each piece as an individual. So to calculate formal charge, it is equal to the valence electrons minus 1/2 of the bonding electrons. So that's like your shared electrons minus the non-bonding electrons. Okay, so some important little hints to help. The formal charge, if you do this correctly, should equal the charge of the ion and the formal charge on a neutral molecule should equal 0. So those are some things to help you out a little bit. And then we're going to say, or talk about how do we find the dominant Lewis structure, because you're going to have to be able to draw multiple structures and figure out which one is dominant. The dominant Lewis structure is generally the one where the atoms bear charges or have charges closest to 0. If I have a Lewis structure in which there are some negative charges, any negative charge, if it resides on the more electronegative atom, it is going to be the more dominant one. It's generally more dominant than the one where the negative charge is on a less electronegative atom. Does that make sense? At some point, you're going to have to go to your periodic table if you're, wondering which one it is, and check the electronegativity. If you have negative charge on a couple different atoms, you're going to have to figure out which one is more electronegative. The one that's more electronegative is generally going to be your dominant.
Is that a Lewis structure in which any negative resides, or any what?
Any negative, yeah. Like you might get a 1 minus or 2 minus on one atom and a 2 plus on another. You'll see we're going to do one. Okay, so what I want you to do now is I want you to take thiocyanate, and I've written it in bonding order for you. Might not be the name the way you memorized it, but, and I want you to come up with the possible Lewis structures. See how many you come up with. Go ahead and move to partner stations and work through it together. When you have all that you think you could come up with, call me over and I will check it.